Welcome to this comprehensive analysis of graph algorithmic structures. Today, we will move beyond basic definitions to explore how we represent graphs in memory, how we traverse them efficiently, and why depth-first search is a foundational tool for complex computational problems. At its core, a graph is a mathematical abstraction defined by a set of vertices, V, and a set of edges, E. Think of it like a map of city intersections. The graph theory approach ignores the physical layout of the roads and focuses strictly on connectivity, which intersections link to which. This allows us to model diverse systems, like social networks or finite automata, using the same underlying logic. The first way to represent a graph is the adjacency matrix. Imagine a square grid. If row I and column J intersected at 1, an edge exists. This structure is mathematically elegant and allows for instant edge lookups. However, it is memory hungry. The space requirement grows quadratically, meaning a graph with 1 million nodes would require terabytes of RAM, making it impractical for large, sparse datasets.
In contrast, the adjacency list is the industry standard for most applications. Instead of a grid, we maintain a list of neighbors for each vertex. This means we only use memory for connections that actually exist. The space complexity drops to big O of V plus E. While checking for a specific edge is slightly slower because we must scan a list, the memory savings are massive for sparse graphs like road networks.
Here is the direct comparison. Use a matrix when your graph is dense, meaning almost every node connects to every other node, or when you need to constantly check if specific edges exist. Use an adjacency list for everything else, specifically when you need to iterate over neighbors efficiently, which is the primary operation in traversal algorithms.
To understand traversal, we use the tricolor abstraction. Initially, all nodes are white. When we encounter a node and add it to our stack or queue, it turns gray. This represents the active frontier. Once we have visited all of a node's neighbors and backtrack, we paint it black. This distinction between gray and black is mathematically crucial for detecting cycles.
We have two primary ways to explore. Breadth-first search spreads like a ripple in a pond, visiting all immediate neighbors first. It is ideal for finding the shortest path in unweighted graphs. Depth-first search, our focus today, acts like a maze solver. It plunges as deep as possible down one path before backtracking. This aggressive strategy is powered by a stack data structure.
Here is the recursive implementation of DFS. It is elegant and concise. We mark the current node as visited, process it, and then recursively call the function for every unvisited neighbor. The post-visit hook, which runs after the recursive call's return, is where the magic happens for advanced algorithms like topological sorting.
While recursion is clean, it can crash your program on very deep graphs due to stack overflow. In production, we use an iterative approach with an explicit stack. A critical nuance here: to preserve the left-to-right traversal order, we must push neighbors onto the stack in reverse order. Since a stack is last in first out, pushing the last neighbor first ensures the first neighbor ends up on top, ready to be popped first. DFS allows us to classify edges based on the color of the destination node. A tree edge discovers a new node. A back edge points to a gray node, an ancestor currently in the stack, which indicates a cycle. Forward and cross edges point to already finished black nodes, representing shortcuts or links between separate branches. DFS generates discovery and finish timestamps that obey the parenthesis theorem. If we treat discovery as an opening parenthesis and finishing as a closing one, the structure is perfectly nested. If node V is a descendant of U, V's time interval is completely contained inside U's. This property allows us to reconstruct the tree structure just from the numbers.
One of the most common interview questions is cycle detection. In a directed graph, a cycle exists if and only if DFS encounters a back edge, that is, an edge pointing to a node currently in the recursion stack. For undirected graphs, we simply check if we see a visited node that isn't the direct parent we just came from.
Topological sorting orders tasks with dependencies, like compiling code libraries. This is strictly for directed acyclic graphs, or DAGs. If the cycle detection finds a loop, a valid order is impossible.
DFS solves this using finish times. A parent task only finishes once all its dependencies have processed. Thus, we list nodes in the reverse order of their finish times.
Implementing complex algorithms like torsions or topological sort iteratively is tricky because standard stacks pop the node too early. The solution is a stack of iterators. We store the node and the index of the next neighbor to visit. This effectively pauses the parent node while we explore children, allowing us to execute code precisely when a node finishes.
Finally, we have iterative deepening. This technique bridges the gap between BFS and DFS. We run DFS with a depth limit, gradually increasing it. It guarantees finding the shortest path in unweighted graphs, just like BFS, but maintains the linear memory efficiency of DFS. It is the preferred choice for massive search trees, such as in chess engines.
To summarize, choose your representation based on graph density. Lists for sparse, matrices for dense. Remember that DFS is more than just a traversal. It is an analytical engine. By leveraging timestamps and edge classification, specifically back edges, you can solve complex structural problems efficiently.